Okay, fourth and final problem, practice problems 8, rotational equilibrium and rotational dynamics. Okay, in this one you can see it's a little more involved. We have to take more aspects into consideration, and we have to draw a couple of free body diagrams so we can see what's going on individually with each of these parts. In this problem, we have a cylindrical 5 kilogram reel with a radius of 0.6 of a meter and a frictionless axle that goes through there. It starts from rest and speeds up uniformly as a 3 kilogram bucket falls into a well. Making a light rope unwind from the reel, the bucket starts from rest and falls for 4 seconds. So in this problem, they're going to ask us for 3 solutions. First, what is the linear acceleration of the falling bucket? Okay, this arrow over here. How far does the bucket drop? And then finally, what is the angular acceleration of the reel, being, of course, driven by the bucket and the rope? So first off, we look at the relationship that says the moment of inertia of a reel is I equal to 1/2 mr squared. And you can find that relationship in your textbook, and it's based upon the geometry, in this case, of a cylinder. Very flat cylinder, but a cylinder nonetheless, more like a disc. So 1/2, that mass, 5 kilograms, times 0.6 of a meter squared, gives us a moment of inertia of 0.9 of a kilogram meter squared. The next step then is applying Newton's second law to the falling bucket, okay, not last law. So we have 29.4 newtons minus the tension in the rope is equal to the mass, 3 kilograms, times the acceleration tangentially or linearly for the bucket and or the spinning reel. Then Newton's second law for the reel gives us the angular value, tau, the torque, is equal to the tension times the radius, which is equal to the moment of inertia times the angular acceleration, which is equal to the acceleration tangential divided by r. So we just worked our way through the conversions from torque to a value that has moment of inertia. So from that, we can move the terms around, knowing that what we're solving for here is a value associated with our knowns. So the moment of inertia we just solved for, 0.9 of a kilogram meter. We don't know the tangential acceleration, but we do know the radius then of that disk, 0.6 of a meter squared. So what we're going to try to do then is solve one in terms of the other. We've got a value here that has the tangential acceleration, and we have a value for tension. So let's see how we can put one into the other. So solving equations 1 and 2 simultaneously then gives us, looking at the first relationship that we got up here, number 1, and the second relationship where now we can substitute our values into the relationship. So this becomes 29.4 newtons is equal to 3 kilograms times the tangential acceleration plus 2.5 kilograms times the tangential acceleration, okay, and then 3 kilograms plus 2.5 kilograms times the tangential acceleration. So the only unknown we're left with then, by combining these two terms, then is the acceleration tangential. And so combining the terms, moving them around, we end up with 5.35 meters per second squared downward. Okay, so we've got that acceleration straight down. B, how far does it drop? Now we have to go back to one of our motion equations. Since we're dealing in the up-down, the y direction, the change in the y direction then, as we saw from the earlier chapters, is equal to the initial velocity times time plus 1/2 of the tangential acceleration times time squared. This term goes to 0, and we're just left with then the values of tangential acceleration, and time squared, which gives us a distance now of the bucket dropping then 42.8 meters. The last part of the problem then, what is the angular acceleration of the reel? All we have to do is rely on the relationship that says the angular acceleration is equal to the tangential acceleration divided by the radius of the reel. Place those two values, we end up with 8.91 radians per second squared. So we've solved for all three of the requirements of the problem. We relied on our values here in our free body diagrams for the reel and for the bucket, and the fact that we were solving for tangential acceleration.